All right, so what we want to talk about is some progress that we've made in the types area. So I'll do a quick reminder. So here, Y stands for Yoneda. So we've talked about the Yoneda embedding before. And so what this represents is we do the final calculation is growth and dec of sub of Y. So we'll do a category of elements construction on all the sub-objects of the Yoneda of the theory. And so what we want to do is we'd like to, because Yoneda is going into set represents our container logic. So the theory, the monad and the models represent the category, the categorical framework where we're modeling the operations that come from the theory of computation. So the term language is here, and then because we're taking a model in set, that's where we're getting our container logic. And what we want to do is we want to be able to change out the container. But in order to do that, we need this thing here, to be enriched in the container. So it turns out that John Power has done a study of essentially when you can change the base. So instead of having the base for the monad be set, you can change the base to some category which is monoidal closed and locally finitely presentable. So that's a lot to unpack. Mike and I have had to kind of, bash our heads against what locally finitely presentable means. It's not as intuitive as you might expect. So for example, finvect, so the category of finite dimensional vector spaces, is not locally finitely presentable, but vect, where you don't have a bound on the dimensions, is locally finitely presentable. So that gives you an example of what we might consider, the kinds of V's that will replace set. So it's a little tricky. The category of monoids is locally finitely presentable. So mon could be here. So, but essentially, what happens is you get a V theory. You get a V. So the shift is, so we go from Vy. So this is Vy. So this is a V version of the Yoneda. And we go into VCat. So the category of V enriched categories, V functors, and V natural transformations. And then this shifts from being set to V. And that will give us enough structure. To interpret not only the term constructors, but logical operations which are coming from V as opposed to coming from set. So this thing is already set enriched because by construction. So we want this thing to be V enriched. So we use Power's construction. So this is changing the base of the monad that is associated with the language, the syntax of the term calculus. And then that so this thing is theory op, the V theory op. So it's automatically V enriched. And then we do a V Yoneda. So we're realizing the structure in V in terms of the Hom sets in V. Then we can take the subobjects to go to the category post sets. So this is going to, in the same way that this gives us a view of, Yoneda gives us a view of functors in terms of Hom sets. This is going to give us a similar of V functors in terms of V gadgets. And so whatever operations live on V. So again, remember, we're interpreting logical operations like and as intersection on set, logical operations like or as union on set, and so on and so forth. So if this is like the freely generated linear category, then we can interpret logical operations like the linear, the multiplicative of linear, the tensor will be the tensor that lives here in V. The additives, will be interpreted in terms of the additives that live here, and so this is the general shape that we have. That allows us to interpret a wider range of logical operations. So that's what we've been looking for. It turns out that there still has to be some kind of coherence relationship and between the theory and the container. So although it's not a distributive law, there are still some coherence constraints that have to be imposed, and so we're investigating those. But this is the shape. This will do the trick. It will allow us to have both logical operations that arise from the term language and logical operations that arise from a container. So it looks like, so this was Christian's original construction, and it looks like, it has legs in the sense that we can extend and expand it beyond just the set logical containers. So that's big progress. The next step is to go and do in-depth calculations for a variety of well-known examples. So the biggest one, of course, is that we want to take theory to be the row calculus and V to be we don't need set because namespace logic is derived from set. Here we would want to take linear logic and potentially vect to look at possible quantum interpretations. So that would give us a quantum logic over a row, which would be quite interesting. Linear would give us, an updatable database with certain kinds of constraints. But that gives us a nice crisp set of examples that are relevant to our chain. Of course, we want to look at other standard examples, lambda calculus and or SKI operators, and potentially some other calculi that are of interest. But this is now the shape. So this can replace the idea of just a distributive law. And it was important to relax the distributive law idea because the containers have to be very, very set-like for the distributive law to work. So that's been the hurdle that we've been up against to have the level of generality that we wanted. I mean, this is the examples that we got were interesting from certainly compelling enough to consider going deeper. This construction here, Christian's construction, is good for all the different theories, right? So now you get a logic for every kind of computational theory. And then, but this is what gives us the computational theory variance together with the container variance, so that you can get additional logics like that. And then just to remind everyone, if this is a little too abstract, let me just remind everyone from the simple examples, right? So if we have a very simple computational language, so just monoids, so M and N, so I have to have an identity. I have to be able to have some generators, right? So G comes from the generators from the monoid, and then I need to be able to do monoid multiplication, right? So that's a very simple computational language, right? So, and then so that gives you monoid expressions, and then you have a set of equations that are going to hold over these things. So you have that E star M equals M equals M star E. And you also have that M1, oops, sorry, this should be little m. And you also have that M1 star M2. So if you do that multiplication first, and then you do this multiplication, that's the same as if you did M1 after having done M2 star M3. All right, so these are the syntactic expressions. These are the equations that we use to whack down, and then our formulae. So I'll just give the formulae. Let's see, how about T, so I don't have to S and T. So S and T will be our formulae. So then that would be, if we were just doing sets, right, that would be true or S and T, or not S. So that's a simple example, but so that part comes from the container, right? And then we have E, E, and again, this is a logical operator that corresponds to this constant, right? So maybe I should italicize it or something to distinguish the other two. Then we have G, like the E's, right? So they're all logical operators. So they're lifting the terms to formulae. And then we have S star T. So that's an example of the container is separate from the terms, right? We can see that this part just comes from set, and this part just comes from the theory part. So hopefully that helps you connect what's going on here with what's going on in the categorical models, right? So this part is theory, and this part here, this part is the theory, this part is the set part. And then the next bit, so something like after MS would mean that it'll ultimately be similar to this in this setting, but it might not be, say, in the row calculus setting. but this part comes from the behavioral piece of the theory. So that's not in this theory here, right? This would be a set of rewrites. So for example, if we took the Chinese monoid, which has a rewrite system which always drives every term to a normal form. So the rewrites of the Chinese monoid would be a separate theory. And then what we do is we encode that. We make a new theory, say theory plus. So we encode that by encoding the theory of graphs directly in adding that to this theory. And then that theory of graphs allows us to interpret this the modal operators. So that's that's what's how this thing decomposes. So hopefully that makes a certain amount of sense for folks. The big hurdle over the last several months has been to see if we could take this construction and generalize this component of it to be a more general container. So V represents that container. We use John Powers' V-enriched Levere theory construction to get a V-enriched version of TH, which then allows us to do a V-Uneta embedding. And then this part remains the same if you want subtyping. So that's the construction. And as I said, the next step is to run this over several examples to see if we get sensible examples. And then the next step after that is to connect that with the proof theory work that I did last year. So last year I came up with a nice way of generating a proof theory from a rewrite system, from interactive rewrite systems. So these are rewrite systems that don't have any heating rules. So anyway, so that's kind of a summary of where we are and the work to date and how it all fits together. The aim is to get good models of type systems like this. And now we can map a type system like this into a construction like this. So that's our categorical model. So hopefully that makes sense to folks. Any questions, comments?
Yeah, Greg, I have a question. So so this is for the behavioral types, and I guess it could also be applied for LSFS as well, but it's primarily for behavioral types.
Well, let's try to make sense of that. So behavioral type, what OSLF does is it generates spatial behavioral types for any computational system. So when I talk about behavioral types for Rolang, we have a solution in the form of namespace logic, but the thing that we have been pursuing, the aim or goal that we have been pursuing, is to generalize the way namespace logic arises for Rolang to a kind of an algorithm that when you give it any programming language, not just Rolang, you give it any programming language, it will generate a similar kind of type system for that programming language.
Right. Mm-hmm.
Okay. Right. So this is a proposal for the final structure for OSLF. So this map here is in, or yeah, just to be super precise and clear. So from this map, we can take the growth and deconstruction. So in another, writing it a different way. All right, so we get integral of sub so integral of sub of vy. Yes, of vy. All right, so this is the final, or the candidate proposed for the final OSLF construction. So this little thing here generates a particular category. And in this category, we can model all of these things. So this thing here is that thing. And this thing is an example of a toy programming language, right? So it's the programming language of clocks, right? You have the generators, which are the, 12, 1, 2, 3, 4, 5, blah, blah, blah. The identity, which is no time has passed. And this is, applying a rotation of the hands to a rotation of the hands. So this is a little toy programming language, and this is a type system generated over this toy programming language. Mm-hmm. And this thing here says how to interpret or model this programming language. I mean, this type system for this programming language. So the V part is this line in the type system. The TH part is this part, or this line in the type system. And then this part comes from enriching TH with the rewrites of the programming language. So you can now, and you can replace this with JavaScript, and that would change this line. Or you could keep the programming language the same and change this from set to the free linear category, and that would change this line. It would now be linear logic instead of Boolean logic. So that's the idea. It's an algorithm that has 3 inputs: the syntax together with the rewrite system. So that's 2 parts that come from here, and a container. So that comes from the V part.
Okay, so yeah, this was helpful in understanding, I guess, the bigger picture. So since we're creating OSLF, which is broad and encompassing all languages, Rolang is one of the many languages. So it by default can utilize the OSLF in its behavioral types.
That's exactly right. So we have a by hand algorithm for namespace logic. So I did that calculation by hand. This calculates namespace logic not by hand, but completely algorithmically.
Okay.
Yeah. So once you encode this construction, then you never have to do namespace logic by hand again. It's a program. You input the various pieces, and it spits out your type system and the type checker.
Okay. Yeah, I've with our previous discussion, I feel like I've got a better handle on what namespaces is, and I actually wrote an article on that. Now I have to kind of take what I know there and think about, this idea of now we have an algorithm that can generate the namespace logic. I have to kind of work through what that means.
Okay, so yeah, so let me. There's a piece of the puzzle that needs to be articulated before they're easily connected. So, monoids, as a theory of computation, don't really have a direct connection with names. Now, there's a way in which that's not true, but I won't go into that in this discussion. But in particular, what they don't have is any form of abstraction. So monoids don't have a lambda abstraction. They don't have a for comprehension, and they don't have other nominal phenomena that we normally associate with names. When your th here supports nominal structure. So if for th I put the lambda calculus, or I put the pi calculus, or I put the rho calculus, or I put the ambient calculus. So when your th supports nominal structure, then your logic will have to manifest the nominal structure here. And when you're, so like in the pi calculus, names are opaque. The only thing that you can really say about names in the pi calculus is freshness, right? So the new operator guarantees. So at the term level, you have a new operator which guarantees that the name, in new x p, the x is fresh from all other names, not just the names local to p, but from all other names globally. That's what the new operator at the level of th provides. When you lift that operator to the level of types, so you're going to go up a level, so that's going to come out here. That becomes a freshness property. So you can now talk about, this name is fresh from these other sets of names, not just terms. And so that's when the logic properly begins to become a namespace logic, except that the only property that you get is freshness, which is not, it's powerful, but it doesn't say anything about the interior structure of names.
Okay. Yeah.
Okay. All right.
Yep.
So now when we move to the rho calculus, rho as a th says something about the structure of names. It says that names are quoted processes. So when you lift the term constructors to logical constructors, so you go to this line in the type system, you're going to get a bunch of constructors for names as logical connectives, which now give you proper connectives for namespaces. But that will now be generated completely algorithmically. We don't have to know anything about the semantics of names or the semantics of the rho calculus. We don't have to have any intuitions or cleverness about any of that. It comes out of this algorithm right here.
Good. Yeah, that helped me further in my understandings. Thank you.
I appreciate the questions. I hope I'm giving answers that are useful for people. Jim, did that help you understand namespaces better?
I guess don't see any operational semantics in the name that you make with a new. I guess that's my issue.
So there isn't a, how do I say this? New shows up in the syntax, at the level of syntax. And then there are a set of equations that it supports. In particular, new x p is the same as new x p. And then new x new y p is the same as new y new x p. And then the one that is really impactful for operational semantics is that new xp, parentheses around that, par q, is going to be the same, assuming that x is not free in q. Then that means that you can now do new x p par q. So those two things are the same. So that impacts your that impacts your operational semantics, because the COM rule is going to take place on a free X, right? So we're going to have a for Y from X, P in par with a send something on X. All right. But now if I have closed up X on one side of that, right? So I've put a new X around the for comprehension, for example. Well, X has got to be free in Q, or the COM rule wouldn't have applied in the first place. Now, if I close up X on the left-hand side of that COM rule, they'll never interact, because I can never get the send something on X into that new bubble, right? And so that's going to impact all of the graphs that are generated by evolution using the COM rule. So that's how they interact with each other. Here, what we've left implicit in all of this, like if we're going to make it completely explicit, you start with a th that is just your syntax, right? And then you enrich that with a, say, th plus. As the plus, there it is. With a th plus. So th plus is we add to the syntactic theory the theory of graphs, right? So you have a theory that it supports source and target, and then you have some equations that are around to interpret, an arrows only approach and a few other things like that. But that theory of graphs is going to be the way in which you realize your COM rule and all your other operational semantics. So when you talk about the source of a red X, right? So the left-hand side of a COM rule. All right. So when you have a red X, then the source will be that red X. And when you have a rewrite, the source will be the red X and the target will be the reduced expression.
Let me see if I understand where my problem was.
Okay.
Now, when we do new names, there's no organic structure to the names themselves.
In the pi calculus, yes.
The row calculus in here.
No, in the row calculus, there is organic structure. And there's no new.
Okay, well, in Rolang, we do new.
Because new is a syntactic convenience. We can always decode a new that's the construction that's given in the 2005 paper. I showed.
Okay, so the unforgeable names themselves have an organic structure?
Yes, right. That's why they're called unforgeable as opposed to, I can't remember the other term of art, but unforgeable means that you can't make it. I didn't give you permission to make it, but you can calculate up front all of the names that are generatable. So the names in row calculus are not unguessable, but they're unforgeable. So in the pi calculus with the new operator, you can make names that are unguessable, right? Because they have no structure, so you have no clue as to how you might go about guessing one. Whereas in the row calculus, the names are merely unforgeable. So you can know up front the entire universe of names, but you may not ever have the permission to use one of them. Does that make sense?
Almost.
Okay.
I guess I I don't know how you can make a name that's not guessable. I mean, it would you if you try a whole bunch of
Okay.
combinations.
So think about probability, right? So what if I use Conway games as my source of names? So I can now put Conway games in one-to-one correspondence with the continuum, and now I can build all kinds of sets where your probability of guessing them is zero, right? There's no requirement that the set of names or the collection of names needs to be is forced to be countable. It can be uncountable, right? It has to be at least countable, but it could be bigger than countable. So I pick something that's like the continuum, and then I can show via probability arguments that you could throw darts at the dartboard all day long and never hit the irrational number I'm thinking of. As an
Okay,
example.
got it.
Sure.
But that was a good insight for me in getting understanding, but getting a better understanding of unforgeable names. So unforgeable names, they have structure, so that's why that they're unforgeable, as opposed to being they're unforgeable but not unguessable because
That's
of the
correct. Yeah.
structure. Okay, yeah, that was good.
Yes, and in DAPI we use the prediction of unforgeable names very much.
Yeah. Exactly. Yeah. Yeah. It's an important property, actually.
Interesting.
And I also asked a question in GitHub, but I'll have to read that again about the prediction of registry URIs. I don't know if it's possible, but it could be a tremendous feature for what I'm developing on our chain.
Okay. I'm sorry, I haven't seen it. I'll if you send me a Discord message, I'll take a look.
Yeah. Okay.
All right. So hopefully this makes some sense. This is the key, right? This is what I was trying to talk about today. That line there is what interprets this thing here for all up to higher order algebraic theories. So it's not just Levier theories, but Levier theories that have exponential objects. So that includes the lambda calculus and the pi calculus and rho calculus and things like that. So I can put my maybe not lambda, but certainly pi and rho. So I can put a wide range of realistic programming languages here. I can put a wide range of logical containers here, and then I can do a sub. I can take all the components, the monomorphisms into that, and that gives me subtyping. And so this thing is that is the model where we interpret formulae.
So with this new update or addition for the behavioral types, is there still more research and thinking that you and Mike need to do?
Yes. So as I said, the next two steps are, one, we redo compelling examples, right? So now that we've got a proposed model, we want to look at some compelling examples. So, and I mentioned, a few compelling examples. So we take, for example, the row calculus in this position, and we swap out set for linear, the free linear category. So effectively linear logic. So now we get a namespace logic that has the linear connectives as opposed to the Boolean connectives. So this line gets replaced with the linear connectives. And we look at that logic. And then we replace V with, instead of being linear connectives, we replace it with, say, vect, which allows us to interpret quantum stuff. So we get a quantum logic. So this line gets replaced with a quantum logic kinds of connectives. And then so that allows us to say things about properties, in where we're interpreting this over some kind of quantum system. So those are some examples that we want to run. Once we've got a feel for this part, so this is just the model theory, it's not the proof theory. So then what we want to do is we want to bring in the work on the proof theory side. So this will give us a type checker that is a model checker, but not a type checker that is a theorem prover. So last year I did a whole bunch of work on a proof theoretic construction. So I generate proof systems for theories that have a particular kind of structure. So that's also some cool work, very cool work. So then what we want to do is to relate that work to this work so that we can compare the proof theory to the generated proof theory to the generated or the generated theorem prover to the generated model checker. So we can look at the complexity of doing theorem proving style stuff to model checking style stuff. Both are going to have, like, when V gets really rich, then there are going to be areas where the formulae are too expressive, right? That the model checking or the theorem proving take forever. So we want to understand the complexity characteristics so we can give good guidance for implementers when they're, swapping out for very rich V's, where's the sweet spot?
Okay, right.
Right. And that's what I was saying. I've said many times before. You have a couple of knobs or dials you can twist. You can tune this down so it's not as rich, or you can tune this down so it's not as rich. And you can kind of balance between the two. You can also turn this down a little bit. So then you find this sweet spot of interesting formulae that tell you things that you want to know before you run your programs, but they do so in finite time.
Right.
So that's the additional research.
Okay.
Yeah, it's a long process,
Yeah.
But this is the results here are very, very powerful when we get them right.
And does that work need to be done as far as, I think about implementation and development of behavioral types? Does OSLF need to be created first before the Rolang behavioral types is created? Or
No, namespace logic is completely published. That's been done for ages. That's why we can be proceeding on track for Venus without having this work slow it down. If, on the other hand, this work makes a sudden jump and can give information to that work, then life is even better.
Okay. So with the work and development on the namespace algorithm that we were discussing earlier, with those types of developments, then we could see Rolang behavioral types coming to life.
Again, I've already done an implementation of the behavioral types, right? So this from 2000, there's code that goes back to 2005. So we're getting close to 20 years old.
Mm-hmm.
And then there's the spatial logic model checker, which is also, that is 20 years old. So that code is basically the template for folks
Okay.
that are going to do the behavioral types for rolling. That's
Okay.
more or less done and dusted.
Okay.
What this does is it gives us a much bigger generalization, and the extent to which this algorithmic approach generates a better implementation, right? Eventually,
Okay.
this is going to generate a better implementation than the by hand implementation of the namespace logic paper.
Okay. Okay.
So
Now, yeah, just kind of understanding sort of the roadmap to where we're at and what the progression is. So I have a better feel for that.
So one way to understand this as a metaphor, an analogy that developers will understand, for many programming languages, Scala in particular, the developers of the language implementation wrote the parser by hand. So they wrote both the lexer and the parser by hand.
Mm-hmm.
But it turns out that we've had parser generator technology for a very long time, like 40 years,
Mm-hmm.
right? So instead of writing the parser by hand, you put in a higher level spec and the parser is generated.
Mm-hmm.
In the case of Rolang, that's how we've done it. So we took oh gosh, I'm blanking on the name of the parser generator right now, but it's a very, very powerful one that allows you to target multiple different platforms. It's written on top of Haskell, and we generate the lexer and the parser for Rolang using that tool.
Mm-hmm.
So similarly, namespace logic is like doing the parser by hand. And if we use this, it's like using a parser generator.
Very good. Okay.
Coolio.
Mm-hmm.
Can you
Thanks for
relate
these. Go ahead.
Can you relate the graph that represented by a Rolang program to the namespace logic? Or no?
It depends on which. If you mean the syntax tree, yes, you can. Right. What namespace? All namespace logic is. I mean, it's an ordinary spatial behavioral logic. The reason I call it namespace logic is just because since Rolang has names with structure, all of that structure shows up in the logic as well. But effectively, this line here, there's an analogous line that shows up in namespace logic, which mimics the term constructors and the name constructors in Rolang. So these things detect sets of syntax trees. So you can see that right here. Yeah. S is going to be a set of syntax trees. T is going to be a set of syntax trees. And then you're going to look at all the syntax trees where you've got that's formed by making a star of one of the trees from S and one of the trees from T.
Yeah, I have one more quick thing.
Okay.
I can see with Rolang the operational semantics of concurrency constraints would be evident. I'm not sure how this does that for any language.
So in particular, The reason I focus on monoids is because monoids show up in lots and lots of programming languages. In particular, they show up in all the languages that support parallel composition. So parallel composition is a monoid where the star becomes the vertical bar of parallel composition. E is the 0. And the generators can be thought of as your either the combinators or you know, your building block programs. So this thing is really a fragment of the logic that you get when you apply this to Rho. And all of this is also speaking about parallel composition. And that was the point I've made in many of these discussions where I've pointed out that if you take the formula for primes, so let's grab the formula for primes. So the formula for prime is it's not going to be the identity, and it's not going to be the star of two things which are not the identity. That's the formula for prime. Now, when you replace star with the vertical bar, which is parallel composition, this very same formula for primes means single-threaded. So one of the beautiful and most compelling examples of this approach to logic is that it relates primality to single-threadedness. Right. So this is one of the things that motivates this whole line of investigation. By going up to this level of abstraction, we're now able to show that things that we say about primeness are closely connected to things that we say about concurrency. Right? What same formula, exactly the same formula, picks when star is the vertical bar, it picks out the single-threaded processes. When star is integer multiplication, it picks out primes. Fascinating, isn't it?
Yep.
All right, I gotta go to Dev Stand Up. Thanks so much for your time and attention.
Yeah, thank you.
Thank you.